Preliminaries. In this section, we shall provide formal definitions for graphical games along with other needed definitions, terminology, and notation. We begin with the notions standard to classical. Multiplayer game theory. A multiplayer game consists of n players, each with a finite set of pure strategies or actions available to them, along with the specifications of the payoffs to each player. Throughout the chapter, we use AI to denote the action chosen by player I. For simplicity, we will assume a binary action space, so AI is in the set 0 and 1. The generalization of the results examined here to the multi-action setting is straightforward. The payoffs to player I are given by a table or matrix MI, indexed by the joint action A arrow, which is in 0, 1 to the n, the set of 0, 1 to the n. The value MI of A arrow, which we assume without loss of generality to lie in the interval between the close interval between 0 and 1, is the payoff to player I resulting from the joint action A arrow. Multiplayer games described in this way are referred to as normal form games. The actions 0 and 1 are the pure strategies of each player, while a mixed strategy for player I is given by the probability Pi, which is in the close interval between 0 and 1, that the player will play 0 for any joint mixed strategy. Given by a product distribution P arrow, we defined the expected payoff to player I as MI of P arrow equals to the expectations of MI of A arrow, assuming that A arrow is very close to P arrow, where A arrow is close to P arrow indicates that each AJ is 0 with probability Pj and 1 with a probability 1 minus Pj independently. When we introduce correlated equilibria below, we shall allow the possibility that the distribution over A arrow is not a product distribution, but has correlations between the AI. We use a P arrow with I replaced by Pi prime to denote the vector product distribution, which is the same as P arrow except in the ith component, where the value has been changed to Pi prime. A Nash equilibrium NE for the game is a mixed strategy P arrow such that for any player I and for any value Pi prime, which is in the closed interval between 0 and 1, MI of P arrow is greater than or equals to MI of P arrow with I replaced by Pi prime. We say that Pi is the best response to the rest of P arrow. In other words, no player can improve their expected payoff by deviating unilaterally from an NE. The classic theorem of Nash 1951 states that for any game, there exists an NE in the space of joint mixed strategies. We will also use a straightforward additive definition for approximate Nash equilibria. An epsilon Nash equilibrium is a mixed strategy P arrow such that for any player I and for any value Pi prime in the closed interval between 0 and 1, MI of P arrow plus epsilon is greater than or equals to MI of P arrow with I replaced by Pi prime. We say that Pi is an epsilon best response to the rest of P arrow. Thus, no player can improve their expected payoff by more than epsilon by deviating unilaterally from an approximate NE. We are now ready to introduce the graphical game model. In a graphical game, each player I is represented by a vertex in an undirected graph G. we use n of I, which is a subset or equals to the set 1 to 3 until n, to denote the neighborhood of player I in G, that is, those vertices J such that the edge ij appears in G. By convention, n of I always includes I itself as well. If a arrow is a joint action, we use a arrow to the I to denote the projection of a arrow onto just the players in n of I. Definition 7.1. A graphical game is a pair G-M, where G is an undirected graph over the vertices 1 to 3 until n, and M is a set of n local game matrices. For any joint action A arrow, the local game matrix Mi in M specifies the payoff Mi of A arrow to the I for player I, which depends only on the actions taken by the players in N of I. Remarks: graphical games are a potentially more compact way of representing games than standard normal form. In particular, rather than requiring a number of parameters that is exponential in the number of players n, a graphical game requires a number of parameters that is exponential only in the size d of the largest local neighborhood. Thus, if d is far less than n, that is, the number of direct influences on any player is much smaller than the overall population size, the graphical game representation is dramatically smaller than the normal form. Note that we can represent any normal form game as a graphical game by letting G be the complete graph, but the representation is only useful when a considerably sparser graph can be found. It is also worth noting that although the payoffs to player I are determined only by the actions of the players in N of I, equilibrium still requires global coordination across the player population. If player I is connected to player J, who is in turn connected to player K, then I and K indirectly influence each other via their mutual influence on the payoff of J. How local influences propagate to determine global equilibrium outcome is one of the computational challenges posed by graphical games. In addition to natural equilibrium, we will also examine graphical games in the context of a correlated equilibrium, CE. CE, Ullman, 1974, generalized NE and can be viewed as possibly arbitrary distributions P of a arrow over joint actions satisfying a certain conditional expectation property. The intuition behind CE can be described as follows. Imagine that there is a trusted party that faithfully draws a joint action A arrow according to distribution P and distributes to each player I only their private component PAI. If P is a product distribution as in the NE case, then due to the independence between all players, the revelation of AI does not condition player I's beliefs over the play of others. For general P, however, this is not true. The CE condition asks that the expected payoff to I, if he is obedient, and player's AI be at least as great the amount I could earn by cheating and deviating to play a different action. In other words, in Bayesian terms, despite the observation of AI updating the posterior distribution over the other player's actions, from I's perspective, it is still payoff optimal for I to play AI. This leads to the formal definition below, in which for any given joint distribution P of A arrow over player actions and B in either 0 or 1, we let P AI equals to B denote the distribution A arrow conditioned on the event that AI equals to B. Definition 7.2. A correlated equilibrium CE for a two-action normal form game is a distribution P of a arrow over actions satisfying that for all I which is chosen between 1 to 3 until n, and for all b which is chosen between 0 and 1, the expectation of mi of a arrow, assume that a arrow is very close to p a I equals to b, which is a greater than or equals to another expectation. The expectations of mi of a arrow with I replaced by not b. Under the condition that if you assume that a arrow is very close to pai equals to b, the expectation e of mi of a under the condition that a arrow is close to pai equals to b is over those cases in which the value ai equals to b is revealed to player I, who proceeds to honestly play ai equals to b. The expectation e of mi of a arrow with I replaced by not b, assuming a arrow is very close to pai equals to b, is over the same cases, but now player I unilaterally deviates to play ai equals to not b, whereas the other players faithfully play from the conditional distribution p ai equals to b. It is straightforward to generalize this definition to the multi-action case again. We demand that it be optimal for each player to take the action provided by the trusted party, despite the conditioning information revealed by this action. Remark C offers a number of conceptual and computational advantages over NE, including the fact that new and sometimes more fair payoffs can be achieved, that CE can be computed efficiently for games in standard normal form. So recall that efficiently here means exponential in the number of players, an issue we shall address, and that CE are the convergence notion for several natural no-regret learning algorithms. Fuster and Vora, 1999. Furthermore, it has been argued that C is the natural equilibrium concept consistent with the Bayesian perspective. Woolman, 1987, Fuster and Vora, 1997. One of the most interesting aspects of CE is that they broaden the set of rational solutions for normal form games without the need to address often difficult issues such as stability of coalitions and payoff imputations. The traffic signal is often cited as an informal, everyday example of CE, in which a single bit of shared information allows a fair split of waiting times. In this example, no player stands to gain greater payoff by unilaterally deviating from the correlated play, for instance, by running a light. This example also illustrates a common alternative view of CE in which correlations arise as a result of public or shared random bits in addition to the private random bits allowed in the standard mixed strategies or product distributions of NE. Here, the state of the traffic light itself, which can be viewed as a binary random variable, alternatively displayed as red and green to orthogonal streets, provides the shared randomization.